Yes, having an ungrounded secondary can have a negative effect. In the event of a brush to ground fall, the full 230 volts would be applied across a controller, which could damage it. There are several ways to improve the situation and protect the controller. Firstly, ground the secondary of the step-up transformer. This would provide a low resistance path for the fault current to flow, preventing the full voltage from being applied across the controller. Secondly, install a ground fault interrupter, or GFI. A GFI is a safety device that detects imbalances in current between the hot and neutral conductors. If an imbalance occurs, the GFI will trip and interrupt the power supply. Thirdly, use a controller with a built-in ground fault protection. Some controllers have built-in ground fault protection that will trip the controller in the event of a brush to ground fault. Fourthly, install a surge protector. A surge protector can help to protect the controller from damage caused by voltage spikes. It is also recommended to regularly inspect the brushes and brush holders to prevent worn or damaged brushes from causing a fault. Also, keep the motor and controller clean and free of debris. Lastly, follow the manufacturer's instructions for troubleshooting and repairing the motor and controller. Now let's delve into each of these solutions in more detail. Grounding the secondary of the step-up transformer is a crucial step in ensuring the safety and proper operation of the DC motor and its controller. An ungrounded secondary, as mentioned earlier, can lead to a situation where a fault, such as a brush going to ground, results in full 230 volts being applied to the controller. This can easily exceed the controller's voltage rating and cause significant damage. When the secondary is properly grounded, it creates a defined path for fault currents to flow back to the source. This low impedance path allows for a large fault current to flow, which in turn will cause the overcurrent protection device, such as a fuse or circuit breaker, to trip. This tripping action quickly disconnects the power supply, minimizing the duration of the fault and preventing damage to the controller. The grounding conductor should be sized appropriately according to the National Electrical Code, or NEC, to handle the anticipated fault current. Refer to NEC Table 250.122 for guidance on sizing grounding conductors based on the rating of the overcurrent protection device. The grounding electrode system should also be properly installed and maintained to ensure a reliable ground connection. Now let's discuss ground fault interrupters, or GFIs. A GFI is a highly sensitive device designed to detect even small imbalances in current between the hot and neutral conductors. In a normal circuit, the current flowing through the hot conductor should be equal to the current returning through the neutral conductor. However, if a ground fault occurs, such as current leaking to ground through a person or faulty equipment, this balance is disrupted. The GFI constantly monitors the current flowing in both conductors. If it detects a difference, typically in the range of 5 mA, it will quickly trip and interrupt the power supply. This rapid interruption significantly reduces the risk of electrical shock and minimizes the potential for equipment damage. GFI are commonly used in areas where there is a higher risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. While GFI are primarily intended for personnel protection, they can also provide a degree of protection for the controller by quickly disconnecting the power supply in the event of a ground fault. However, it is important to note that GFI are not designed to protect against overloads or short circuits. For those types of faults, overcurrent protection devices such as fuses or circuit breakers are still required. Next, consider using a controller with built-in ground fault protection. Some manufacturers offer DC motor controllers that incorporate ground fault protection circuitry. These controllers are designed to detect ground faults within the motor or controller itself and to automatically shut down the system to prevent damage. The built-in ground fault protection typically works by monitoring the current flowing through the motor windings. If a ground fault is detected, the controller will trip and de-energize the motor. This type of protection can be particularly effective in preventing damage to the controller and motor in the event of a brush to ground fault or other internal fault. It is important to select a controller with a ground fault protection system that is appropriately sized for the motor and application. Refer to the manufacturer's specifications for guidance on selecting the correct controller. In addition to ground fault protection, surge protection can also be beneficial in protecting the controller from damage caused by voltage spikes. Voltage spikes, also known as transient voltages, can occur due to a variety of factors such as lightning strikes, switching of electrical equipment, or problems with the power grid. These voltage spikes can be significantly higher than the normal operating voltage and can damage sensitive electronic components in the controller. Surge protectors are designed to divert these excess voltages away from the protected equipment and safely to ground. They typically contain components such as metal oxide varistors or MOVs that clamp the voltage to a safe level. When a voltage spike occurs, the MOV conducts and diverts the excess current to ground, preventing it from reaching the controller. Surge protectors are available in a variety of configurations, including whole house surge protectors that protect the entire electrical system and point-of-view surge protectors that protect individual devices. For the DC motor controller, a point-of-view surge protector installed at the controller's power input can provide effective protection against voltage spikes. It is important to select a surge protector that is appropriately rated for the voltage and current of the circuit. Refer to the manufacturer's specifications for guidance on selecting the correct surge protector. Beyond these specific protection measures, regular maintenance and inspection of the motor and controller are essential for preventing faults and ensuring reliable operation. One of the most important maintenance tasks is to regularly inspect the brushes and brush holders. Worn or damaged brushes can cause a variety of problems, including increased sparking, reduced motor performance, and ultimately, a brush-to-ground fault. Brushes should be inspected periodically for wear, cracking, and chipping. If the brushes are worn down to the wear line or show signs of damage, they should be replaced immediately. Brush holders should also be inspected for damage and proper spring tension. If the brush holders are cracked or broken, they should be replaced. The spring tension should be adjusted to ensure that the brushes make good contact with the commutator. In addition to inspecting the brushes and brush holders, it is also important to keep the motor and controller clean and free of debris. Thus, dirt and other contaminants can accumulate inside the motor and controller, causing overheating and reduced performance. The motor and controller should be cleaned periodically with a vacuum cleaner or compressed air. Avoid using water or other liquids to clean the motor and controller, as this can damage the electrical components. Finally, it is essential to follow the manufacturer's instructions for troubleshooting and repairing the motor and controller. The manufacturer's instructions will provide specific guidance on how to diagnose and repair common problems. Attempting to troubleshoot or repair the motor or controller without proper knowledge and training can be dangerous and can potentially damage the equipment. If you are not comfortable troubleshooting or repairing the motor or controller yourself, it is best to consult with a qualified electrician or motor repair specialist. In summary, protecting a DC motor controller from damage due to brush-to-ground faults requires a multifaceted approach. Grounding the secondary of the step-up transformer provides a low impedance path for fault currents, while GFI offer rapid disconnection in the event of a ground fault. Controllers with built-in ground fault protection provide an additional layer of safety, and surge protectors help to mitigate the effects of voltage spikes. Regular maintenance and inspection of the motor and controller are also crucial for preventing faults and ensuring reliable operation. By implementing these measures, you can significantly reduce the risk of damage to the controller and ensure the continued operation of the DC motor system. Remember to consult with qualified professionals and adhere to all applicable electrical codes and safety standards when working with electrical equipment. A 230-volt DC motor operates on direct current, while the incoming power is 208 volts alternating current. The step-up transformer converts the 208 volts alternating current to 230 volts alternating current, and a rectifier within the controller converts the 230 volts alternating current to 230 volts direct current to power the motor. The fact that the secondary side of the transformer is ungrounded means that there is no reference point to ground. In a grounded system, if a fault occurs, such as a brush going to ground, the current has a clear path back to the source, tripping a breaker or blowing a fuse, thus protecting the components. However, in an ungrounded system, the voltage potential flows relative to ground. When a brush goes to ground, the entire 230-volt potential is then applied across the controller components, likely exceeding their voltage ratings and causing damage. The 118 volts and 68 volts readings to ground in the ungrounded secondary are due to capacitive coupling and leakage currents. These readings do not indicate a fault, but rather the voltage potential relative to ground in an ungrounded system. Ground in the secondary provides a stable reference point and ensures proper operation of overcurrent protection devices. The GFI operates by monitoring the current balance between the supply and return conductors. Any imbalance indicates current leakage to ground, which the GFI detects and trips, disconnecting the circuit quickly. This protects both personnel from electric shock and equipment from damage. Surge protectors, also known as transient voltage surge suppressors, protect against voltage spikes caused by lightning, switching operations, or other electrical disturbances. These spikes can damage sensitive electronic components in the controller. Surge protectors divert excess voltage to ground, thus clamping the voltage to a safe level. Routine maintenance is key to preventing failures. Check the brushes for wear, proper seating, and spring pressure. Ensure the commutator is clean and smooth. Inspect wiring connections for tightness and insulation integrity. Regularly clean the motor and controller to prevent accumulation of dust and debris, which can cause overheating and insulation breakdown. Always consult the manufacturer's documentation for specific maintenance procedures and troubleshooting steps. If you are not comfortable working with electrical equipment, seek assistance from a qualified electrician. Electrical work can be dangerous, and safety precautions should always be observed. Remember, this is a simplified explanation, and specific implementations may vary depending on the motor, controller, and application. Always refer to the manufacturer's documentation and consult with qualified professionals for specific guidance. Ensuring proper grounding, using GFI and surge protectors, and performing regular maintenance will contribute to a safer and more reliable DC motor system.